In this next example, we're going to look at finding a power series representation for the function tangent inverse. Now, one way we can approach this is we can look at the derivative of tangent inverse. And for us, we get the function 1 over 1 plus x squared. And therefore, that can remind us that when we integrate that function, 1 over 1 plus x squared, we get the function we're looking to find the power series for, tan inverse of x. So in this case, that's how we'll be approaching it. In order to find the power series of tangent inverse, we'll be integrating the power series of 1 over 1 plus x squared. And to remind you, we approached this same problem earlier by writing 1 over 1 minus x squared as 1 over 1 minus negative x squared. And so its power series was negative x squared to the n. Or writing this as the series negative 1 to the n x to the 2n. We have the power series representation of 1 over 1 plus x squared. Therefore, to get the power series of tan inverse of x, we'll be integrating that function. And hence integrating the power series, negative 1 to the n x to the 2n. Which we can write as c plus, now integrating just the x to the 2n. I'll leave the constant multiple of negative 1 to the n unchanged. So we'll add 1 to the power, divide by 2n plus 1. That'll give us the power series representation of tan inverse. One thing we can keep in mind here is that we can solve for this constant c by substituting x equals 0 into both sides of this equation. So on the left-hand side, if I substitute tan inverse of 0 in for x here, we can get c plus the series negative 1 to the n 0 over 2n plus 1, which of course is just 0. Tangent inverse of 0 is 0. So that gives me 0 for c. So therefore this factor of c here we can remove. And there we have it. We have a power series representation for tan inverse of x. So it's an alternating series, negative 1 to the n, x to the 2n plus 1 over 2n plus 1. So notice here that it's got odd powered terms, and it's an alternating series. So it would start with x minus x cubed over 3 plus x to the 5th over 5, and so on, x to the 7th over 7. And in this case, again, we used the 1 over 1 minus x form to get the power series representation here. Hence, we can say our radius of convergence, which I'll put up here, is the same as it was for the series 1 over 1 plus x squared. So it's the same radius of convergence. Now one thing we could check, because here I believe when we substitute the, so we have the absolute value of x has to be less than 1 here, but if we substitute the endpoints of this interval, negative 1 and positive 1, into the series, we notice that we may get convergent series. In particular, when x is equal to 1, we get an alternating series, negative 1 to the n over 2n plus 1. And so it would satisfy the alternating series estimation, or sorry, the alternating series test, and hence it would be convergent at x equals 1. And let's see, if I were to also test x equals negative 1, we can also verify that at negative 1, let's test negative 1 here. We can work it out. So I would have negative 1 to the n, and then negative 1 to the 2n plus 1 over 2n plus 1. And so when I multiply these two factors, we would get negative 1 to the 3n plus 1 and in this case, because this is still going to be alternating, because we notice that when n is even, we get an odd power here, and when n is odd, we get an even power here. So it's still an alternating series, and so by alternating series test, that would be included in our interval of convergence as well. In this example, we want to look at expressing an integral as a power series. In this case, if we write 1 over 1 plus x squared, at 1 over 1 plus x to the 7th as a power series, then we can try integrating it as a power series. Okay, and just quickly up here, we can work it out. 1 over 1 plus x to the 7th is really 1 over 1 minus negative x to the 7th. So we can substitute negative x to the 7th into our power series representation. And so we have the series negative 1 to the n, x to the 7n, as the power series representation of this function. Therefore, we can integrate that function as a power series. And now just doing the term-by-term integration here of x to the 7th, x to the 7n, we'll just apply the power rule to that x to the 7n factor. And just integrating x to the 7n, we have the series negative 1 to the n, x to the 7n plus 1 over 7n plus 1. So notice here, we could also evaluate this as long as our values of x are in the interval of convergence. So let's just quickly remind ourselves what would be the interval of convergence here. So we know that basically this step that we're doing here is only valid as long as x to the 7th is less than 1 in absolute value. And therefore, if I take the 7th root of both sides, we would get x has to be less than 1 in absolute value. So as long as x is between negative 1 and positive 1, we can integrate on any interval contained in that range. In particular here, if I want to integrate from 0 to 0.5, we can write that, we can approximate that as a power series. So let's write what that would look like here. So the integral from 0 to 0.5 of this function here. Well, using the work that we did in the previous step, we integrated 1 over 1 plus x squared as a power series. And it was something of the form negative 1 to the n, x to the 7n over 7n plus 1 over 7n plus 1. And now we'll evaluate from 0 to 0.5. And so substituting in 0.5, I get negative 1 to the n, 0.5 to the 7n plus 1 over 7n plus 1. Notice that at 0, all the terms will be 0, so evaluating it at 0 is just 0. And now the question is, how many terms of this series do I need to add in order to be correct within 10 to the negative 7? In other words, I want an error that's less than 0.000. So here, let's write Rn, our error. We want that to be less than 0.00006 zeros, and then a 5. Or actually not 5, 1. Right, that's 10 to the negative 7 there. Okay, so we want our error to be less than 10 to the negative 7. That's the desired error. So what we can do is we can use the alternating series estimation theorem to figure out how many terms we need to go out in order to guarantee that Rn is less than, has an error that's less than 10 to the negative 7. When I start writing out the terms here, let's look at the first few terms. So the first term I think would just be 0.5. And then the next term would be minus 0.5 to the power of 8, right? Over 8. And then the next term would be 0.5 to the power of, let's see, 7 times 2 is 14 plus 1, so 15 over 15. And so on. The next term, let's write one more, would be 0.5 to the power of, let's see, 21 plus 1 is 22 over 22. Okay. Now, I have a feeling that these terms are getting very small. So let's check to see if these terms here are going below our desired error. So I'm going to evaluate these last few terms in my calculator to see how close they are to going below this 10 to the negative 7 in our desired error. So what I notice here is that when I evaluated this term here into my calculator, I get something in the order of 2.03 times 10 to the negative 6. So notice that's not quite below that 10 to the negative 7 error that we're looking for. And now this one is, because I think we get something around 1.08 times 10 to the negative 8. So this is now the first term that's going to go below that 10 to the negative 7 desired error. And so using the alternating series estimation theorem, we know that here Rn will be less than Bn plus 1 for an alternating series. Okay, you can remind yourself what the alternating series estimation theorem tells us. And therefore here we can add up these first terms here, and we know that that sum will have an error that's less than this term here. So here the sum of just these three terms here will give us an error. So here I'll say R3 will have an error that's less than R4, or the B4 term here, which is 1.08 times 10 to the negative 8. And that's certainly less than 10 to the negative 7. So therefore we've just got to add these first few terms to get our desired error. And in this case that will be around 0.499513 7. So just writing out the first 7 decimals there, since that was where we know our accuracy will lie.